First of all, let me start by thanking the staff for helping out. And they do just an incredible job every time we have these things. So thank you so much. Yeah. So I'm going to talk about a topic that we have been working on for the last, I would say, 2 to 3 years. It's pretty recent. I was not thinking about this 10 years ago, and certainly not, not before coming to Stanford. So why methane? And I'm going to talk about methane and also talk about CO2 right at the end. Atoms to atmosphere, well, I mean, it's a fancy name. But we're trying to also develop imaging techniques to go down to the atomic scale for things that we're trying to do. Okay, so why methane? This is the atmospheric concentration of methane. And over the last 2,000 years, that's the left-hand curve. And over the last about 100 and something years, the last about 40 years on the right-hand side. And as you can see, much like the CO2 profile, this is going up kind of super exponentially. It's nonlinear. The one on the right-hand side is the more recent one, and you can see there's a leveling off, and then the methane concentration is going up. And no one really knows, frankly, as of now, why this is leveled out. There are lots of theories, a lot of speculation, but it is going up. And the question is, what are the sources of methane? And as you can see out here, there are multiple sources. This is from work of, I don't know if Rob Jackson is here. Rob leads the Global Carbon Project. And you see the circles in yellow are the wetlands that produce methane. There are agricultural waste. Cows produce methane. And agriculture, like rice paddy, produces methane because it's underwater, so there's no oxygen out there. So all the carbon that is there goes into methane. And these are bugs called methanogens that produce the methane that comes out. And fossil fuel production and use, Adam Brandt and others, and including Rob Jackson, they're measuring the methane that is coming out. And Adam has shown that in the western part of the Permian Basin, all the fracking and all are producing like 9% of the methane goes into are lost and emitted in leakage. And so but the biggest part is the agricultural part, so it sort of ties back in some ways to the food. I'm so glad we had 2 food things. I'm a foodie. So, but nevertheless, this is a big deal. And what you may have noticed in the previous chart is that of the 1.3, 1.4 degrees global average temperature rise that we've had, about 0.5 degrees is from methane. And so this is a big deal, but it's different from CO2. This is the radiative forcing curve. As you can see, carbon dioxide is the largest radiative forcing, and methane is, is the second most important. But frankly, it is, it's about half or slightly more than half of the radiative forcing of CO2. And what is interesting is that this is, as opposed to CO2, where the lifetime of the CO2 molecules in the atmosphere, in the circulation, is several hundred years, methane actually goes down. And we'll come back to this. The global warming potential, even though the concentrations are 2 ppm, the global warming potential of methane is very high. It starts off at 120, and then over 20 years or so, it goes down to 84, and over 100 years, it goes down to about 28 or so. Okay, so even though the concentrations are low, much lower than CO2, it's rising, but it's much lower than CO2, the global warming potential makes it pretty deadly. And we'll talk about why it goes down, and that is where the source of the potential solution is. So the short-term effects of methane are really, really important. The long-term effects, well, there's a natural way for it to go down, and this is different from CO2. Okay. So there was a really important paper that came out from Stanford. This is Rob Jackson, Ed Solomon, chemistry department, Matteo Carnello in chemical engineering, and of course, Chris Field. Of methane removal and raising the issue of can we remove methane from the atmosphere because of the climate impacts. Methane is it's a very symmetric molecule, and so and there are no dipoles in it. Dipoles are charge separation, and so because of that, it doesn't stick to anything, and it is very, very inert. So if you leave methane, it doesn't easily combust right away. Although the proposal out here was to somehow figure out how to combust with oxygen and produce CO2 and water. This is what happens when you burn natural gas in your stove, right? So, and there's a huge amount of heat that is given out, which is how we warm many of the homes and do cooking, et cetera. Except that there's a problem out here in the atmosphere. The heat of combustion is such that when you burn it, it sustains the reaction and you can keep going. But you can't burn the atmosphere. And so the problem out here is that you have, this methane is a very stable molecule. It would naturally, one would think that it will combine with oxygen and form CO2 and give out a lot of heat. But there's a problem. There's a big hill to climb, which is, in chemistry, is called the activation barrier. And there's a big hill to climb. And that hill suggests that unless you raise it to about roughly 1,000 degrees Celsius, it's not going to combine with oxygen to produce CO2. So the natural thing, should we be scorching the atmosphere? No, that's like boiling the ocean. We cannot do that. So how do you oxidize? How do you activate methane and oxidize it at room temperature? So this is where nature comes in. Nature has shown us the way. But because of this, it becomes really difficult. There are different ways of doing it. I just want to show you methane concentrations that are coming out from natural sources. I showed you the sources of methane before. And this is another work from Rob Jackson with one of my students, Max Kessler, and Rob's student, Sam Abernethy, of the concentration, the million tons per year of methane that are coming out, and at different concentrations of methane. So from oil and gas, it's pretty high concentration, 10⁵ ppm. You have waste, and you got coal bed methane. The methane is leaking out at about 1,000 ppm. And you got all this livestock waste and wetlands and rice and fresh water, which is much, much lower, all the way to 10 ppm, and the atmosphere is 2 ppm. We know how to combust things above 1,000 ppm. So we know how to do that. But below that, we don't have any technology. And above things, if you have enough concentration, then you can collide, you can raise the temperature, and you have enough heat given out that you can sustain the chain reaction. But below this is very, very hard. Yet, nature has figured out how to do this at 2 ppm. That's what happens in nature. So the question is, how does it do it? Turns out the mechanism is different. It has to be different. It uses UV light, and UV light is absorbed by ozone, which, by the way, is a potent greenhouse gas. It is absorbed by ozone, and when it absorbs UV light, it breaks it up into oxygen molecule and oxygen atom. Oxygen atom is highly reactive because it's a single atom moving around. It's trying to find a pair. So these oxygen atoms can collide with oxygen molecules and form ozone back again. Once in a while, it collides with a water molecule and reacts with it. And there's enough water molecules in the atmosphere to form what is called an OH radical. What is an OH radical? It splits up water to form a hydrogen, and then it forms this OH with a little electron sticking out. And this is a radical. This is often called free radicals. In our body, we get free radicals when you have UV light and all of that, and that's bad for health because it's very reactive. It damages our DNA and many other things. But this is what nature uses. It forms a radical which is highly reactive, and that's the only way we know how to activate methane at room temperature and not need 1,000 degrees Celsius. And methane activation, the CH bond, the first CH bond of methane activation is one of the hardest problems in chemistry. People have dedicated their careers in trying to find out how to activate methane. And nature has shown that this is how it does at room temperature. Once it hits the methane molecule, it knocks off an hydrogen and forms water. So OH grabs a hydrogen, gets activated and forms water, and it leaves behind something called a methyl radical, which is CH3 with a little electron hanging out. Okay, that's a little green thing. And so when this methane, now it's activated, now it can react. The methyl radical collides with oxygen molecule. There's enough oxygen out there. And there's a whole chain reaction that happens. I won't go into the details, but eventually forms CO2. So that's how nature uses. And the question we asked is, can we emulate nature? Well, one way to do that is put a lot of ozone in the atmosphere, which is a really bad idea because it's a greenhouse gas. So how else can we form these OH radicals? And the way we are looking at this is work in progress, is to take a semiconductor like titania. Titania is dirt cheap. It's there in paints. But it is a semiconductor which absorbs UV light. It's found in powder like this. But it has to be of a certain size. And this is 10 nanometer scale. And this is the size. It's about roughly 25 nanometers in size. And it's very important for that size to happen. And then this absorbs UV light. And as soon as it absorbs UV light, it excites an electron and leaves behind a hole. So it energizes the electron and activates it. And it leaves behind a hole. It turns out both the electron and the hole are pretty active. The hole reacts with water molecules, and we have shown, and not us, a lot of people have shown, it forms an OH radical. But you cannot have only one reaction. It has to have the other reaction, otherwise this will not work. The other reaction is to take the electron and do something with it, which nature doesn't have to do. In this case, we have to actually add a little metal, little dust nanoparticles on it. And once you form the metal, the oxygen molecules can grab this electron and form this oxygen molecule radical, O2 minus, which we have now seen with electron parametric resonance, and I won't talk about that. But it forms something called the OOH radical, grabs a hydrogen and OOH radical. It turns out that both are interesting. We've found two radicals. This is not Berkeley, this is Stanford. There are a lot of radicals out here. But nevertheless, we have shown that this can activate methane. I won't go into the data. This is some paper that we published, that you can not only form CO2 now, you can convert methane to CO2, but if you put a little coating of glass around it, very thin coating of glass, it turns out it's porous enough that you can form methanol, you can form formaldehyde, all kinds of things show up. But you can control this by the thickness of the glass, and you can eliminate the glass and go towards CO2. So now we have control. Then we asked the question, and I challenged the two grad students, Max Kessler and Richard Randall, and a postdoc who's now a staff, there's Gang Wang out there. Can we oxidize methane at 2 ppm, which has been a technological gap, at room temperature? And it turns out we just demonstrated, we haven't written this up yet. This is now, instead of titania, it works for titania, this is zinc oxide, which is also a semiconductor. It absorbs light, the zinc oxide particles, and if you put a little dust of silver, it actually acts up and it activates much better. And you can get 2 ppm methane, and you can oxidize it, goes down. As soon as you turn on the light, if you turn off the light, it goes away. So this is UV, and this UV radiation is the equivalent, the intensity is equivalent of the UV part of solar radiation. And the idea is that if you could figure out how to do this, you can then throw some particles out there and actually oxidize methane, whether it is a natural gas leakage that is happening, or a wetland, or maybe in the atmosphere. So Richard Randall, not Richard Kessler. Richard Randall did this study with Rob Jackson and me to see if you were to do crop dusting and throw these particles, how much would it cost and what are the scientific targets for the performance of this? And he said that you can get to about $50 a ton of CO2 equivalent if you can get to 3% quantum yield. I just want to spend just a minute on the CO2 part. This is similar to the curve that David showed. On the y-axis is the rate of emissions. On the x-axis is time. I call this scale versus speed. And if you were to maintain the temperature below 2 degrees, you got to have negative emissions of CO2 equivalent. And by the mid-century, it has to be about 10 gigatons. This is the horizontal line, 10 gigatons of CO2 per year. And the question is, how do we get there? Now, CO2, like methane, is dispersed. Anything you want to do, either with CO2 or methane, you need energy. Whether you separate it out, or if you want to upgrade CO2 into some other molecule, you need energy. And that energy, instead of trying to concentrate the whole atmosphere through some machines called direct air capture, you would rather use distributed forms of energy. It's already there. And that's photosynthesis. And it's funny that I'm talking about crops. This is what David was also talking about. If you look at the crop residues, it roughly captures about 10 gigatons of CO2 per year worldwide. This is mostly grains, which is rice, barley, corn, and wheat. And many places, they burn it to renew the field. That's the cheapest way to renew the field. If you could convert some of these biomass into recarbonizing the soil, that would be great, but we want to make sure that there's no microbial degradation of this. Otherwise, you get CO2 and methane back. And this process has to be dirt cheap because you're making dirt. So how do we do that? Well, there's a lot of work going on right now, both here and elsewhere, of collecting biomass. We know how much it costs to collect, transport them, shredding. But the biggest chunk of the cost is to carbonization of this. And there's pyrolysis techniques, torrefaction, hydrothermal carbonization, microwave pyrolysis. They're all high temperature processes. And it's around $50 and north about $100 a ton of biomass. And we asked, this is a joint postdoc with E and me. We challenged him to see, can you figure out a way to reduce the temperature? Because you're not going to get 10 tons of biomass going through, or 10 gigatons going through a heater. That's going to be very difficult if we want to scale it. So this guy, this is Divya Chalice, who just finished a PhD from Berkeley and joined us, in a matter of 6 months or so, has now figured out how to make room temperature biochar. This is rice and wheat, and he's taking waste. If you have waste lying around, please let us know, because he's trying to convert everything into biochar at room temperature. And we are really excited about this. Let me end by, this is my research group in my backyard. I still have a research group going on, about 12 students and 6 postdocs. And the last picture I want to show is last year, my former students threw a party for my 60th birthday. Yes, I've turned 60. And this is a picture of a symposium that we had in this room. And this is out in the patio out there. And you can see a few faces that are familiar. That's Steve Chu out there. That's Each Way. I think that's over there. And I don't know who else is here. My wife is over there. Most of them are my former students and postdocs who are all around the world right now. So thank you so much.